Hello everyone. So today we're going to be showing that the Lorenz transforms leave the spacetime interval invariant. This is another question that you might find in your course, and we're going to use the equation for Griffiths for the Lorenz transforms that we get in equation 12.8 for your Griffiths E&M book. We're also going to use the interval delta S squared, which is given in equation 12.36 for Griffiths, and we're just gonna go from there. So we want to show this. So we're gonna have to find the components for each of them and figure out what the interval is. So let's do that now for the left-hand side. And we know that delta S squared is equal to C squared delta T squared minus delta x squared minus delta y squared minus delta z squared. Now, this comes from equation 12.36 in Griffiths, but if you haven't used the Griffiths textbook yet, then I would recommend that you find whatever course notes you have on this material, and in there somewhere you're going to get this equation that you can use to compute the answer. So great, we have this invariant component, and what we find is that delta S squared is equal to C squared, and now we're going to separate delta T into the two different components of T. So T1 minus T naught squared minus x1 minus x naught squared minus y1 minus y naught squared minus z1 minus z naught squared. So now we're going to show how if we apply a Lorenz transform in some arbitrary direction, that when we compute delta S prime squared, we're going to get essentially the same value of delta S squared. So what we need to do here is we're going to have to apply the Lorenz transform to each of these components of time. And then we're going to compute through and find that they should be equal to one another. So again, we're going to use the equations for Lorenz transform that we have. So here, x bar basically just means x prime, and we're going to plug in these equations into delta S. So computing this now, we get T1 is, let's see, we are here, so T1 prime is equal to gamma times T1 minus V over C squared x1. Then we're going to do the same thing for T0. So T0 prime is equal to gamma T naught minus V over C squared x naught and we're going to apply the same equation for the x component, y component, and z components. So just computing that now, we get x1 prime is equal to, going back here to this equation, that's equal to gamma x1 minus v t1. Similarly, we do the same thing for the x naught equation. So x naught prime is equal to gamma x naught minus v t naught. And we're going to do the same thing for the y and z cases. But again, these cases don't really change. So we're just going to keep them the same. y1 prime is equal to y, just as the equation said. And z1 prime is equal to z1, just as the equation says. Similarly, y0 prime is equal to y0. and z0 prime is equal to z0. So the strategy here is to find the interval for delta s squared now, using the same formula that we found. And then our goal is we're gonna try and simplify this formula so that, once we simplify it, we'll be able to show this quantity is, inherently true. So computing that now, we're gonna have to find delta t prime, delta x prime, delta y prime, and delta z prime. So let me just write that for you out explicitly first, just so we have a good gauge about where we're heading. C squared delta t prime squared minus delta x prime squared. So our task now is to compute values for delta t prime, delta x prime, delta y prime, and delta z prime. So here we go. That's the goal now, and we're going to start in doing this computation. So here we go. Delta t prime is equal to t1 prime minus t0 prime. And if we're going to get the square of that, then we're going to square this whole thing. So computing this out now, we're going to get gamma t1 minus v over c squared x1 minus gamma t0 minus v over c squared x0 squared. So computing through the algebra now, we find that we can factor the gamma out of both. So we get t1 minus v over c squared x1 minus t0 plus v over c squared x0, I believe. Correct. Squared. So expanding all of this out now, we get gamma squared is equal to t1 minus t0 squared. We get these terms squared minus gamma squared v over c squared x1 minus x0 squared. This term and this term squared. Now, we've taken this together and we've taken this together. So what we need to do is we need to get the cross terms between each of them. What you would do, the manual way, is just expand all of this out and then factor terms. That's one way of doing it, but we're going to use a quick little shortcut here, just because we can. So the cross terms here we're going to get is minus 2 times gamma squared, v over c squared, and then we're going to have the first term minus the second term. Essentially what we're doing is we're doing a quadratic multiplication of these two terms here. So from that we get t1 minus t0, x1 minus x0. And that is our value for delta t prime squared. So again, doing the same thing now for delta x prime, we get gamma x1 minus x0 where's our x primes? They are here. Okay, so I'm just going to copy this down just so I don't forget what they are. Put them over here, and we can delete them later. So we have x1 prime minus x0 prime squared, which is gamma squared, factoring the gamma out. x1 minus v1 t1 minus x naught minus v t naught squared, which is equal to gamma squared x1 minus x naught minus v, oh yikes, minus v t1 minus v t naught squared, I believe. Correct. Yes? Yes, okay. So from this, we're just going to expand it out the same way we expanded these terms out, treating this as one component of the quadratic and treating this as another component of the quadratic. So again, just to be more explicit, we're going to use the FOIL method. First, outer, inner, last. So delta x prime squared is equal to gamma squared x1 minus x naught squared minus gamma squared v squared t1 minus t naught squared. And then again, the cross terms as we expect. So 2 gamma squared v x1 minus x naught t1 minus t naught as expected. Now, again, we're going to do the same thing for delta y prime squared, which is just, we're going to use these values. So y prime is equal to y, and z prime is equal to z. So this is equal to y prime 1 minus y naught prime, which is exactly equal to y1 minus y naught. That's equal to delta y squared. Forget the squared values. And again, doing the same thing for delta z prime squared, z1 prime minus z naught prime. And that's exactly equal to z1 minus z naught squared, which is equal to delta z squared. So great. Now we have to compute our value for ds. And let's just compute that out now. So let's write ds again, delta s, and we want that to be equal to delta s prime squared. That's what we're trying to show. And we're using delta s prime squared, and that's equal to c squared delta t prime squared minus delta x prime squared minus delta y prime squared minus delta z prime squared. And we have all our values for t prime, x prime, z prime, y prime over here. So we're just going to use these values. Great. So let's just take the t prime component first. Let me just copy it. Save myself in the writing. And we're going to rewrite this because we noticed that by doing this, we're actually able to write delta t prime that's equal to gamma squared delta t squared minus gamma squared v over c squared delta x squared minus 2 gamma squared v over c squared delta t delta x. So that's the equation for delta t. And we're going to simplify the same equation for delta x. So let's just put this over here. And now get the equation for delta x. Delta x prime squared is equal to gamma squared delta x squared minus gamma squared v squared delta t squared plus 2 gamma squared v delta x delta t. Great. So once again, we're going to put that equation on the right-hand side at the very top. And now essentially we're going to take these equations and we're going to substitute them into our values here. So delta s prime squared is equal to c squared gamma squared delta t squared minus gamma squared v over c squared delta x squared minus 2 gamma squared v over c squared delta t delta x minus delta x squared, which is this equation over here. So delta x squared is gamma squared delta x squared minus gamma squared v squared delta t squared plus 2 gamma squared v delta x delta t plus the last two components, so it's delta y prime squared, which is just delta y squared, and delta z prime squared, which is just delta z squared. Again, applying the Lorenz transforms, we know that the y and z components don't change. Great. So just making sure that I have all my minus signs correct. There should be a minus sign here in front of delta x. So this should be in brackets, I believe. Yep. Okay, great. So expanding everything out now. C squared gamma squared delta t squared minus gamma squared v delta x squared minus 2 gamma squared v delta x delta t. That's just this stuff over here. Minus gamma squared delta x squared plus gamma squared v squared delta t squared plus 2 gamma squared v delta x delta t minus delta y squared minus delta z squared. And we find that these two terms are going to cancel out because they're off by a factor of minus sign. And then we're going to factor all the other terms together. So let's factor this delta t squared term. That's equal to gamma squared c squared plus v squared. And the delta x squared is equal to minus delta x squared gamma squared. And then I believe we have I believe this should be a squared here. Yeah, okay. So we get delta x squared, gamma squared, and then the other component is 1 minus v squared over c squared. And then we have minus delta y squared minus delta z squared. So again, we're going to factor out c squared from the delta t squared part of the equation. So delta s prime squared is equal to c squared, delta t squared, gamma squared, 1 plus v squared over c squared. No, I'm off by a minus sign somewhere for sure. It should be a minus. Is this a minus? Right, because this is a plus. Yeah, so I made the mistake by putting a minus there, but it should be a plus. So then this becomes a plus, and therefore this becomes a plus over here. And yeah, then you get c squared minus v squared as expected. And then I believe this is a plus as well. Yeah, perfect. Minus delta x squared, gamma squared, 1 minus v squared over c squared, delta y squared minus delta z squared. Now, we know that gamma is equal to 1 over the square root of 1 minus v over c, v squared over c squared. So therefore, gamma squared is equal to 1 over 1 minus v squared over c squared. So again, we're going to substitute these values in for gamma and evaluate the expression. So then 1 over gamma squared is equal to 1 minus v squared over c squared. And that's exactly what we have here and here. So just computing delta s now equals c squared, delta t squared, gamma squared, 1 over gamma squared minus delta x squared, gamma squared 1 over gamma squared minus delta y squared minus delta z squared. Therefore, finally, when we do the computation, we get c squared delta t squared minus delta x squared minus delta y squared minus delta z squared. And we find that this actually is exactly equal to delta s squared. So delta s prime squared is equal to delta s squared, as expected. Now, if you're following through very closely, I believe I might have made a few minus errors in these equations over here. So I will post the exact solution as a screenshot in the description below. So you can just refer to that, and that's 100% accurate. Perfect. So thank you very much, everyone, for watching, and I will see you for the next video.